Uh, Welcome everybody to today's IAMP One World Mathematical Physics seminar. It's my great pleasure to introduce today's speaker, Gordon Slade from the University of British Columbia. And the title of today's presentation is Mean Field Tricritical Polymers. So let me say that, as usual, the seminar will be recorded and made available on YouTube. And I now leave the floor to Gordon. Thank you very much, Gordon, for being with us.
Thank you very much, Marcello. It's really a pleasure for me to be here and to have this opportunity to talk about the mean field tricritical polymers. So this is joint work with Roland Bauerschmidt from the University of Cambridge. And let me start with the physical motivation for the problem that I'm going to be talking about. It's got to do with polymer collapse. So you should think about having a polymer, linear chain polymer in a solution. In this image here, there are multiple polymers, and in the model that I'll be describing, there's just one, but basically the basic situation is the same. So you have some control parameter that can be changed, like the temperature or the acidity of the solution. And what can happen when that change occurs is that there's an abrupt transition from the polymer being in an extended phase like this, where it could be modeled by a self-avoiding walk, to a collapsed phase, where it becomes a compact object and tries to be in contact with itself rather than in contact with the solution. So the way that Flory put it in his book on polymer chemistry from 1953, that the better the solvent, the greater the swelling of the molecule. Conversely, the poorer the solvent, the smaller the molecule. So there's a kind of a value judgment as to which one of these pictures is the better one. This is the good solvent on this side where the polymer is in an extended state. And this is the poor solvent where the polymer is collapsed. And the thing is that this transition takes place abruptly, so that as the temperature, say, is changed, the transition takes place at a critical temperature, which is called the theta point. And that's a tricritical point, and I'll try to explain what that means. And moreover, in 3 dimensions, which is obviously the interesting one from the point of view of polymer chemistry, or at least it is an interesting one. 2 dimensions is also interesting, but 3 dimensions is where you typically have your polymers, that at that specific tricritical point, the theta point, the polymer behaves mathematically like a simple random walk. So I'll discuss this in more detail, but this is the situation that we're trying to model here. And well, I mean, there's been a model of this for a long time. It's the model that I'm going to be discussing is a continuous time random walk. Sorry, I've got some issue with the Zoom there. Okay. It's a continuous time random walk. And let me introduce it in some generality first. There's 2 examples that I want to discuss. So let G be a transitive finite graph. So the vertex set of the graph is lambda and the edge set is E. And I really only have 2 examples in this talk. One is where G is a toroidal approximation to ZD. And I'm really interested in the case D equals 3. And ultimately, we want to take the thermodynamic limit where the finite volume approximation to Z3 becomes the entire cubic lattice. And the second example, which is the mean field one, is where G is the complete graph on n vertices. That just means that we have a collection of n vertices and there's an edge between every pair of vertices. And ultimately, we want to take the limit as the size of the system n goes to infinity. So we have this graph, and I want to consider a random walk x on the graph. It's a continuous time random walk, and the way it operates, it's just simple random walk. So when it's at x, a vertex x in lambda, it waits an exponential amount of time. So there's a probability distribution with density e to the minus t. And when that random variable, when the bell rings for that random variable, then the random walk moves to one of its neighbors uniformly chosen. For the case of Z3 and the torus, there'd be 6 neighbors, and it picks each neighbor with probability 1/6 and steps to it. And the steps are independent, so what it does next is independent of what it did before, and the waiting times are all independent as well. So another way of thinking about this is that X is the continuous time random walk on lambda, whose generator is the Laplacian on the graph. And the Laplacian is defined in this way. So if we have a function on the vertices of the graph, then the Laplacian of f is a new function, which is just the average of the difference. I mean, you look at the difference between f at a neighbor of x and at x and take the average over the neighbors. So the degree of x is the number of neighbors of x, and this means that y is adjacent to x. So that's the Laplacian. So this is the continuous time random walk. And associated to that, there are some random variables that are going to be important. So the first one is the local time of x, of the random walk at a point x in lambda up to time t, is the amount of time spent by the random walk at the point x up to time capital T. So this indicator is just 1 whenever the random walk is located at x, and otherwise it's 0. And what this integral does is it just collects all of the time spent at the point little x up until time t. So that's the local time at x. Of course, if I add up over all of the different x's, the local time at x, I'm just going to get t. That's just common sense, but you can also see it by inserting the definition of the local time as an integral and then interchanging the integral and the summation. And when you sum over x, the indicator that the random walk is at x, you're going for any fixed t, you'll get 1, and so this integrates to t. Second random variable that's important is the L2 norm squared, the self-intersection local time, so-called. So if you do this sort of maneuver with L squared, you write 2 integrals, then you can do the sum over x. You'll have an integral with respect to s and an integral with respect to t. And when you do this sum over little x, you'll just end up requiring that the random walk be at the same place at times s and t. And so this is a measure of the time that the walk spends intersecting itself. And similarly, if I look at the L3 norm cubed, I'll have a triple integral of an indicator for the walk to be at the same location at time s, time t, and time u. So this is a measure of the amount of time that the walk spends in a triple intersection. And then we're ready to now define the main objects in the model. So it's a 2-parameter model. G and nu are real variables, positive or negative. And the 2-point function is defined in this way. So I'm going to spend a minute or so unpacking what this definition says. So 0 and x are 2 vertices. 0 is the origin of our graph, say, and x is some other vertex, or possibly at 0 as well. And let's look at this expectation first. So this E0 represents the expectation for the simple random walk started at 0. That's this capital X. So we're averaging over the random walks here with this expectation. The walk starts at 0, and we're forcing the walk at time t to be located at little x. So that was the second point in the 2-point function. 2 points are 0 and x here. And then we're weighting the random walk by this exponential factor here. So this L local time cubed, which is getting summed, is a measure of the amount of triple intersections, 3-body intersections. So that's because there's a minus sign up here. When this is big, the capital X is weighted less, and so that's a repulsive interaction. And On the other hand, there's this competing interaction because I'm really interested in the case where G is negative, although it's allowed to be positive. I'm most interested in the case where G is negative. So this is really an e to the plus the absolute value of G self-intersection local time. And so that's encouraging two-body attraction. So there's a two-body attraction and a three-body repulsion. And so these are competing with each other. If I was going to be just studying directly the polymer model that I began with, I would prefer to just study this for fixed t, but that's not what we'll do. We'll look at the Laplace transform of that instead. And so there's this e to the minus nu t, and then we integrate with respect to t. So nu is a chemical potential that's controlling the walk length. So when nu is large, then that makes t want to be small. And so we have shorter walks. Nu could even be negative here. This will still be a convergent integral in finite volume, no matter what G and nu are. Okay, so there's the two parameters, the G, which is controlling the self-attraction, nu is controlling the length, and that's the two-point function. The susceptibility is the sum over vertices x in lambda of the two-point function. And when you sum that, you just forget about where the walk ends. So the sum over x only appears here, little x. And when you sum that, it becomes 1. And so this is the susceptibility. So we're interested in the two-point function and the susceptibility and how these things behave in the infinite volume limit as functions of G and nu. Other observables are the expected length and the density. So the length of x we'll think of as being this, basically as this t. So this is a probability density function when normalized by the susceptibility, which is just its integral. And we'll use that as the density for this random variable L, which is the length of x. So the expected length is what you get by integrating this density against t. And well, one way to get the t is to just differentiate chi with respect to nu. That will bring down a t with a minus sign. So this dot here represents differentiation with respect to nu. And so the expected length can be computed from the susceptibility in this way. And the density of the walk is the limiting value, assuming the limit exists as the volume goes to infinity, of the length divided by the volume, the expected length divided by the volume. So these are also functions of G and nu, because G and nu enter into the density of the length. And our goal in this talk really is to understand how these functions, the expected length, the density, the two-point function, and the susceptibility depend on G and nu. And here's a kind of generic phase diagram for what you might expect. So in the shaded region is what we'll call the dilute phase. This is the extended phase. Well, let me call it the dilute phase. So here the susceptibility is finite, the density is 0. And in this region, the unshaded region, the susceptibility will be infinite and the density will be non-zero. The two regions, the dilute phase and the dense phase, are divided by this curve here, which has two parts to it. So this dashed line is a second order curve across which the density is continuous. So the density is 0 here, and it's also approaching 0 as the second order curve is approached from the dense phase. Whereas this is a first order line across which the density is discontinuous. And this point here is maybe the most interesting point in the diagram. That's the tricritical point, or the theta point, which separates the first order part of the curve from the second order part of the curve. So this is the kind of picture that one might expect, and we'd like to try to verify it in some case. So let me say something about what's known on Z3. So let's consider the model on Z3 now. So we are we have this continuous time random walk on a on a torus, three-dimensional discrete torus, which is approximating Z3. This is the thermodynamic limit that sends that torus to the infinite volume. Otherwise, this is just the same two-point function that we were talking about before. So X is the nearest neighbor continuous time simple random walk on the torus. And as I mentioned at the beginning, the prediction is that at the tricritical point, the attraction and the repulsion exactly cancel, and the two-point function behaves like the green function for simple random walk, which is just the inverse Laplacian. And here's a theorem whose proof I'm not going to be discussing here, but it's a recent theorem with Roland Bauerschmidt and Martin Lohmann, who was a postdoc at UBC at the time. He's now working for the Allen Institute for Artificial Intelligence in Seattle. And I'm just going to state it loosely, but it says that for Z3, there is a tricritical point in the sense that at that point, if you choose G and nu correctly, this two-point function up here in infinite volume decays with X like the Laplacian. So it's asymptotically some amplitude divided by X to the D minus 2, which is with D equals 3. So it's 1 over X. And in fact, this theorem holds much more generally for n-component spins for a phi to the 6th model. So I like this theorem. As I say, I'm not going to talk about the proof, but when we proved it, we wanted to prove more, and we didn't succeed, partly because we didn't really understand the phase diagram at that point. And so this was our motivation with Roland Bauerschmidt for trying to do a really thorough analysis of a mean field model of this this kind of tricritical phenomena in order to map out what the expected, or at least for map out in the mean field model what the phase diagram would look like. And the upper critical dimension for the tricritical point is 3. And so what we're seeing in terms of tricritical behavior in the mean field model, we expect it also applies in the three-dimensional case. So it gives us some guidance as to what we might try to prove. So I'm going to switch now to the mean field model. So we're on the complete graph, and it will be for the rest of the talk. So lambda, the vertex set, I'll just take to, it has endpoints in it. I'll call them 0, 1, up to n minus 1. And of course, we're interested in letting n go to infinity eventually. And we define the two-point function, the susceptibility, the expected length, the density, the same way that I've described previously. So there are these two parameters, G and nu. G is a measure of the two-body attraction. Nu is the chemical potential. And we define the effective potential. So this I'm kind of pulling out of the hat right now. We'll see where it comes from later on, but it's a function of a single real variable, actually non-negative, into R. And it's defined in this way. V of t is t minus the log of 1 plus little v of t. And little v of t is given by something that maybe looks a little familiar here. There's e to the minus s cubed minus gs squared minus nu s, which is like e to the minus local time cubed, e to the minus g local time squared, e to the minus g local time, I mean e to the minus nu local time. And then there's some other stuff in this integral. There's a root t over s, and there's this modified Bessel function of the first kind. If you're familiar with the Curie-Weiss model, which I think many of you are, this is the analog of the function, which is like v of phi squared would be, with some betas, phi squared minus log of the hyperbolic cosine of phi squared. So it's going to be playing a similar role to that effective potential for the Curie-Weiss model. Just by definition, when you put t equals 0, you see that v of 0 is 0. So there's a t here, which makes this little v equal to 0 at t equals 0. So you have log of 1 is 0, and this is 0. So v of 0 is 0 by definition. And the reason that I mentioned this V is because all of the interesting quantities for the mean field model, the model on the complete graph, can be expressed as integrals involving V. So for example, for the 2-point function, now by symmetry on the complete graph, the 2-point function has only sort of two values, G00 or G0 something else, which we might as well take to be 1. So G01 is given by a one-dimensional integral of e to the minus n v of t, n is the volume, which is going to go to infinity, times this kernel, f01, which is given by this form. It's not terribly important for the moment what it is. It is explicit, and it's a function of the, it's an expression in terms of the effective potential. So everything here is very explicit. And similarly, it's possible to write the 2-point function at coinciding points, G00, or the susceptibility, or the expected length, in terms of an integral e to the minus n times the effective potential times some f, which is different depending on which one of these observables you're interested in. But they all have this form with some f. F may depend on n, as it does here, but in a way that's very explicit. Once you know this, you can then apply the Laplace method for the evaluation of the asymptotic behavior of an integral with a large parameter in the exponent like that, in order to determine what the asymptotic behavior is of the observables, and to understand how that is affected by the value of g and nu, which is what it is that we're trying to do here.
Excuse me, I forgot what is G01, F01. Could you recall?
So F01 is this, and it's written here, but G01 is the 2-point function. So the 2-point function is, well, here it's on Z3, but the 2-point function was defined like this. So yeah, I mean, it's good to know what this is. It's the basic quantity.
So here this is the graph, the complete graph. So 01 is just the generic. I mean,
it's a pair of distinct points.
It is just a pair of distinct points. Okay, thank you.
Yeah. Any other question? Right, so G01 is when the points don't coincide. G00 is when they do. Those are the only two cases on the complete graph. Chi can be expressed as G00 plus n minus 1 times G01. The expected length is then, given in terms of the derivative of chi with respect to nu divided by chi with a minus sign, and so on. So let me remind you about the Laplace method for the evaluation of the asymptotic behavior of integrals with a large parameter in the exponent. The book by Olver is a very good reference for this. So there's two cases that are relevant for what I'm going to be describing. One is the case where this function v that shows up here in the exponent has a uniquely attained global minimum at 0. So I'm always interested in the case where v of 0 is 0. And that's the only case I'll be discussing. So here, if 0 is the uniquely attained global minimum, with v behaving like t to the mu for some positive mu at t equals 0, and if f is, first of all, it should be integrable, so that this f should be integrable at 0, so it should be diverging no worse than 1 over t. So you want to have t to the lambda minus 1 with lambda positive, so that this integral makes sense. In that case, this is asymptotic as n goes to infinity to some gamma function, depending on lambda and nu, some amplitude. What really matters here is the power of n. So it's 1 over n to the lambda over nu. So lambda and nu are describing the behavior of f and v at t equals 0. So that's the case where you have a uniquely attained global minimum at 0. If there's a unique global minimum somewhere else at some positive t0 with positive curvature at that point, then you have exponential behavior. So v of t naught will be negative if it's the global minimum, because v of 0 is 0. So v of t naught has to be smaller. So this is actually growing. It's exponentially growing with n. And then there's some factors here that are not so important for us, and 1 over the square root of n. So there's a big difference in the asymptotic behavior of these integrals depending on whether v has its global minimum at 0 or not. In one case, you don't have exponential decay or exponential growth, and in the other case, you do have exponential growth. So in order to understand the behavior of the 2-point function, which is given by one of these integrals, where v is the effective potential, we need to figure out what is the minimum structure of the effective potential. And well, we can just plot it. And let's look at a couple of cases here. So g, which is here, it's minus 2.7. So we're in the, the g is negative, so it's giving us some attraction, 2-body attraction. There's always the 3-body repulsion. And here we have 2 different values of nu. And what has happened is that the effective potential, which is being plotted in blue here, as nu increases from 1.2 to 1.4, it has a negative global minimum here, which will rise until by 1.4, it's the global minimum is now at 0. So somewhere in between here, the this minimum went positive. This corresponds to the dense phase, and this corresponds to the dilute phase. Another thing that can happen is that the effective potential can look like this, so that now the global minimum is again occurring at some non-zero value, but in a different way than it did here, where first here the first derivative is positive, here the first derivative is negative. First derivative is positive, and but then it comes down and has a negative global minimum at 4.22 when nu is 4.22. As we increase nu, then that global minimum will rise, and there's sort of a different behavior here in the sense that the global minimum goes from being some value, which is around 1.7 or something here, to 0 abruptly. And that corresponds to the first order part of the phase diagram, as we'll see. The tricritical point is the point where v has derivative 0 and second derivative 0 at the origin. So here's the definition of the phases. So in the dilute phase, we have a positive first derivative and a unique global minimum at 0. So that's this case and this case here. In the dense phase, there's a unique global minimum at a strictly positive value, so that the global minimum will be negative. And that's this case here and this case. So these are both in the dense phase. The first order curve corresponds to the transition that takes place for g values when nu increases from this situation to this situation. Whereas the second order curve corresponds to this kind of a transition as you increase nu. And the tricritical point is sitting right at the middle of everything. So here's a picture of the phase diagram with those effective potentials plotted at the same values that I had just plotted before. So these magenta points here are the ones that we were looking at previously. And for reference, the black dashed line corresponds to where the effective potential has 0 first derivative at 0. And the red dotted line is where the second derivative is 0 at 0, second derivative of the effective potential. And the tricritical point is the point where those two curves meet, where both derivatives are equal to 0. This is the second order line here. And the blue line is the first order line. So what we proved is that the density is 0 up here in the dilute phase. It's non-zero down here in the dense phase. It's continuous across this second order curve, discontinuous across the first order curve. So as you approach the first order curve from above, the density will be approaching 0 because it's always 0 in the dilute phase. Whereas if you approach from below, it will have a non-zero limit. Some easy calculations tell you that how do you find these curves? These moments play a role. So m sub k is this sort of kth moment of this function, e to the minus s squared minus gs squared minus nu plus 1s. And just by simple calculations, you find that v prime of 0 is 1 minus the 0th moment, v double prime of 0 is the is the 0th moment squared minus the first moment squared. The tricritical point is the point where both of these derivatives are equal to 0, which corresponds to m0 equal 1 and m1 equal 1. The phase boundary, consists of this black dashed line, the lower part of it, together with the blue line. It's continuous at this point here, the tricritical point, but it's not twice, it's differentiable, in fact, but it's not twice differentiable. So some sample results of the kind of theorems that you can prove here. We proved that in the infinite volume limit, the expected length behaves in this way. So if you're in the dilute phase, the expected length is just finite. It's just this number, which is expressed in terms of the effective potential. This is its derivative at t equals 0, and this is the new derivative up here is what that dot is. Along the second order curve, there's some amplitude, and then it's growing like the square root of n. At the tricritical point, it's growing like n to the 2/3. And on the first order curve and in the dense phase, it's growing like n. This v dot of t0 is non-zero. So remember that the density was defined by the limit of the ratio of the expected length to the volume. So you would divide this by n and let n go to infinity to get the density. That will be 0 in the dilute phase and on the phase boundary. And it's just this v dot of t0 is the density on the first order curve in the dense phase. We're interested also in what is the critical phenomena associated with the tricritical point. So as the tricritical point is approached from the dense phase or along the first order curve, you can calculate how it goes to 0. And it depends on the nature of the approach. So here, n is the normal to the phase boundary. M is the direction of the approach, and S is the distance along a line segment in the direction of approach. So if you're approaching in a non-tangential direction, then the density will vanish as a square root of the distance from the tricritical point. Whereas if you approach tangentially, it's linear. And the amplitude for that linear asymptotics depends on whether you're approaching from the first order side or the second order side. And also if you approach along the first order curve, there's another amplitude. So all of these things can be computed. So basically you can compute everything. All right, so that's what I wanted to say about the results. What I haven't explained to you is where does this effective potential come from? So if I go back, we had these formulas for the 2-point function and so on in terms of one-dimensional integrals involving the effective potential. So I haven't told you yet how to prove this theorem, and that's what I want to do next. What I've tried to explain so far is that once you have those formulas, those integral formulas for the 2-point function and so on, that it's possible to derive just by relatively elementary asymptotic analysis what is the asymptotic behavior of the observables. So the way that we proved that theorem about the integral representation of the observables in terms of the effective potential is via a supersymmetric representation of the polymer model that I want to try to describe here. So first there's I want to introduce a Grassmann algebra. It's a very simple one with just two anti-commuting generators, which I call psi and psi bar. And elements of this Grassmann algebra, I'll call them forms, are written K, and it's a linear combination of these generators. So you can either have no generators or either one of the generators or the product of the two generators. Higher multiples will give 0 because these generators are anti-commuting. And the coefficients are functions on R2, which I'll write as functions of u and v, going to kj of u and v, where j is 0, 1 bar, 1, or 2. And in fact, it's more convenient to think of u and v as being the real and imaginary parts of phi. And so rather than u and v, I'll prefer to write phi and phi bar. Phi is u plus iv, and phi bar is u minus iv. So we have that Grassmann algebra. And we'll say that one of these k's is even if there's no psi bar or psi term. So if k1 and k1 bar are equal to 0. So that leaves little for k to be. It's just k0 plus k2 psi bar psi. A favorite example is this phi squared. That's the name of the k. It's phi bar, or u squared plus v squared plus psi bar. And if we have a function, we'll define a function of an even form k by its Taylor expansion in the so-called fermionic part of k. So this is the purely bosonic part of k. This is the fermionic part of k. And in this case, if f is some function like e to the minus t, then f of phi squared will be f of phi bar plus f prime of phi bar times psi bar. This is the definition of how you evaluate f on a form. And because of the anti-commutativity of psi bar, I could also write it this way with a minus sign. In fact, we need the Grassmann algebra with 2n anti-commuting generators. So every point in lambda is going to have a pair of generators. So there's going to be psi I bar for each I in lambda. And the top degree form, the one sort of that has the most fermions in it that you can put, is when you multiply them all together. So psi1 bar psi1 up to psi n bar psi n. And that will have some coefficient k2n, which is a function of u and v, where u and v are each in Rn. And the integration of a form is defined like this. So if you want to, this is the notation for the integral over R to n d phi of k is defined to be a multiple 1 over pi to the n. Not very important about the pi factor, but it has to show up somewhere. This is where we put it. And then the Lebesgue integral of the coefficient k2n of the top degree part of k. That's the definition of the integral of a form k. So for example, to go back to our function f of phi squared here, if we want to do the integral of that in the case where we just have the two generators, according to this prescription, there would be a 1 over pi because n is 1, integral over R2 And then we're supposed to look for the top degree part of f of phi squared, which is this minus f prime phi bar of psi bar. Take the coefficient, which is minus f prime of phi bar. Phi bar is just u squared plus v squared, and then integrate it. And if you convert to polar coordinates, then that simply, t is like r squared in polar coordinates. That can be written in this way. And just by the fundamental theorem of calculus, it's f of 0. So there are a lot of beautiful formulas in this subject. And this is one of them, that if you integrate f of phi squared, you just get f of 0. So there's an isomorphism theorem, so-called, which relates the random walk model to these Grassmann variables. And it's quite general. So on any finite graph and with any generator, we're interested specifically in the case where delta is the graph Laplacian, but it doesn't have to be for this formula to be true. It's extremely general. LT is the vector of local times. That means that, so I want to think of it as a vector, LT comma x, where x is in lambda, is the local time at x. And if we have an integral like this, so this is a one-dimensional integral with respect to t, of an expectation for the random walk with generator delta on lambda, starting at x, we're forcing the walk to end at y at time t, and we're taking the expectation under that restriction that the walk be at y at time t of some function of the local times, which is what we have in our 2-point function, right? I mean, we have this e to the minus, we have this exponential involving local time L2 norm squared, L3 norm cubed, and so on. So such an integral, which is what we have as for our 2-point function, can be written as one of these Grassmann integrals, where the generator for the random walk appears up here. For us, that's the Laplacian. There's f evaluated at phi squared, where phi squared is just the collection of these phi bars plus psi bar at every point. So LT is a vector, right? It's LT comma x. We have a function of that. We evaluate that function now at these forms using the rule I described via Taylor polynomials in order to figure out how to evaluate a function. And this pairing up here in the exponent is given by this combination. So this theorem was proved by Bridges and Munoz-Maya about 30 years ago. Ideas in physics were predating that, in particular by Parisian, Surla, and McCain, who independently in 1980 came up with formulas like this. And so we're going to use that. And another thing that we need is an elementary calculation where here we have phi bar, psi bar, so which are the variables that are already appearing up here. But in addition, there's another constant or like block spin, you might think of it, field, psi bar and psi bar. So psi bar are like the phi's and psi bar are like the psi's. And on the complete graph now, so this is a lemma for the complete graph, which is our mean field setting. This exponential factor here with the pairing can be written as an integral with respect to this variable z of e to the minus z minus phi squared, where z minus phi squared is given by this, this sum. So this is something which is straightforward to prove via the definition of what this integral on the right-hand side is. I won't go through the calculation, but we have this lemma. So
excuse me, do I understand correctly? Zeta are commuting and psi are anti-commuting.
The phi's are bosons, they're commuting, and the psi's are fermions, they're anti-commuting. Same with the zetas are commuting and the xi's are anti-commuting.
Thank you.
Yeah, right. So we have both. And there's a symmetry between them, which is this supersymmetry. And so here's where the effective potential comes from. So let me define this function Pn of the vector of local times. I'm going to write it as a product. You could also, of course, it's a product of exponentials. So it's also the exponential of the sum, which is the way that we saw it in the 2-point function. Let's think about it that way for a moment. Let's move the product up into the exponent. Then you have the exponential of the sum of the local time cubed, g times the local time squared, nu times the local time. That would just be nu times t. When you do that sum over x of the local time, you recover the t. So this is exactly the kind of factor that shows up in the definition of the 2-point function. Let's look at the 2-point function at coinciding points here. So this first equality is just the definition. We had the integral over t of the expectation for the simple random walk starting at 0 and ending at 0 at time t of this product here. So there's e to the minus local time cubed, g times local time squared, nu times local time, which is just nu times t. So the factor e to the minus nu t has been moved into the p here compared to where it used to be, but this is the same formula that we had previously. And now this is exactly one of these integrals here that shows up in the isomorphism theorem, where the f now is just given by the p sub n. So this first equality is the definition of the 2-point function. The second equality is the isomorphism theorem, which writes one of these integrals involving expectations of functions of local time in terms of a Grassmann integral. So this is just exactly the statement of the isomorphism theorem that we were just looking at. And then we apply the lemma to rewrite this e to the minus phi Laplacian phi as this z integral. So, and then interchange the order of the integration. So this exponential factor got turned into this one together with the integral with respect to z. Now, the beauty of this is that this 2n-dimensional integral completely factorizes. It factors into a product of n integrals over R2, because this exponential is just an exponential of a sum that factorizes, and this p has been written here already in factorized form. So it factorizes, and actually every one of the integrals except for the one corresponding to the point 0 is the same integral. The factors are all the same. So when you do that factorization, we'll take the n-1 integrals that were identical and write them as the n-first power of e to the minus v of z squared. So e to the minus v of z squared will just be defined to be what one of those common factors is. And then there's a special one because of this phi 0 bar phi 0, which is specific to the point 0 and is not appearing for the other factors, plays a special role. But in fact, it's also possible to write this integral as e to the minus v of z squared times another kernel. So
Gordon,
yeah.
can I ask? So this is, of course, for a complete graph, but
this is the complete graph. Yeah.
Yeah.
That's
but
right.
I guess that you have something similar for general graph, for general Laplacian, right?
So for general Laplace, the way that the theorem for Z3 is proved is this. So this is like a kind of decomposition of the interaction of the covariance defining the integral into a sum of two terms. Whereas in the case of Z3, there's a decomposition into what is effectively infinitely many terms. And so you have to do infinitely many renormalization group steps. This could be regarded as a single renormalization group step.
Mhm.
And for the complete graph, you only need to do one.
Okay. Mhm. Thank you.
So, sorry, Gordon, can I ask you a question?
Yeah.
But this lemma for the representation of the exponential of minus phi Laplacian phi, this is something you also use in the renormalization group approach for
No,
the,
no, this is for the complete graph, this one.
Mhm. So there is no analog of that for like what you do in the blocks in the block spin analysis. No.
Right. It's more complicated. So we use a decomposition of the covariance into, well, n scales if we're talking about a Laplacian if we're talking about the model on a torus, say of size L to the n for some L.
Mhm. Oh, so let me confirm. So yeah, I'm sorry. So how about this isomorphism theorem? So this is true for
this is
any
true
Laplacian.
on any graph.
Okay.
Yeah.
So this lemma is for the complete graph. Okay.
Yeah. The theorem is true for any finite graph, and we certainly use this theorem for the analysis of the tricritical point, and also for like weakly self-avoiding walk in dimension 4.
Okay.
Many other problems. It allows one to basically completely forget about the random walk model and just work with these Grassmann integrals, which look familiar to like it looks like a spin system.
Yeah.
So
yeah, thank you.
Right. So what I was saying was that what we've seen now is that this 2-point function, at least for coinciding points, can be written as a one-dimensional integral with respect to this z, which has got a boson in its complex conjugate and a fermion in its complex conjugate that we're doing an integration with respect to e to the minus n v of z squared times some explicit kernel, which we could write down here, but I'm not writing it down. And what remains is to say what is v. How do we actually calculate v? So we had a formula for v, which is the logarithm of this integral here. So e to the minus v of z squared is given by this integral, and so we just have to do the integral. But we know how to do the integral. So the definition of e to the minus v. One thing is that we use supersymmetry in a way to simplify things so that we can forget about the fermion in the argument of v. It's enough, it turns out, to just look at the bosonic part. And so if you write down what this is, just remembering the definition from the previous page, it's this integral, where p is this function with the e to the minus, there's e to the minus s cubed, e to the minus g s squared, e to the minus nu s, and so on. And you just use the definition of what this integral is. So you want to look for the highest degree part, that is the psi bar part of this integral. And I'm not going to go through the steps in detail here, but really it's just a calculation that takes a few lines where you follow the instructions for how you compute one of these. It's just a two-dimensional integral. How do you compute it? And you remember what your definition of the modified Bessel functions of the first kind are. And you find that after the smoke clears, you end up with this expression. And so if you put this zeta squared equals t, and you use the fact that this p tilde, which is just p times e to the minus s at 0 is equal to 1, you get the formula that we had before. So I wrote it before in terms of the logarithm, but there it is.
Maybe this is a stupid question. There was a cubed power, and then it disappeared. So there is no 3.
No, it's here.
Yes, but then there is a sequence of equalities. I mean, it's
in the p, right?
Okay.
It's in the P, yeah. So P has a cube power in it.
Okay, thank you.
Okay, so my time is just about up, and that concludes the discussion of the model that I wanted to tell you about. But there's another version of this problem which has been studied in the literature. I'm not going to be discussing all of the literature about this, but the interacting self-avoiding walk is something that has been studied quite a bit as a model of this polymer collapse. So it has several variants. The most basic one is where you have a measure on n-step strictly self-avoiding walks in which the probability of a walk is proportional to e to the minus g times the number of nearest neighbor contacts. So this is the number of pairs of times where the walk is at distance 1 from itself. So if g is negative, then the walk will get a reward for having nearest neighbor contacts. And so it's a self-avoiding walk, but so that makes it want to be extended, but this reward for contacts makes it want to be compact, and the competition of the two is what is responsible for this collapse transition. And there has been a lot, here are a few references. There are many other, there's a much bigger literature on this, but specifically for this model, Daniel Ulci proved almost 20 years ago that for d greater than 4 and small negative g, so that means very little attraction, behaves as if there was no attraction at all. So that is that the collapse doesn't take place for small g, small negative g, if d is greater than 4. And you proved that using the Laplace expansion. There's another model which is similar, but with a different kind of proof, again using the Laplace expansion, that for d greater than 4 and small negative g, again, collapse doesn't take place. In d equals 4, there's a renormalisation group analysis that says that for small g doesn't do anything either. The problem for weakly self-avoiding walk is interesting even for d equals 1, and that has been analyzed in some depth. There's recent work on the interacting prudent walk, which I won't go into the definition of it. There are other, there's a big physics literature on this, especially from the 80s. Duplantier and Salur worked on this a lot in dimensions 2 and 3. Thomas Perlberg and company have worked on this problem. So many different people have worked on it. I think that's basically what I wanted to say. So thank you for your attention. I've listed some references here. So the tricritical paper for the complete graph, which is what I was mainly talking about, appeared in this new journal, Probability in Mathematical Physics, last year. The Z3 work is in the Journal of Mathematical Physics from last year. And if you're interested in the isomorphism theorem, I recommend chapter 11 of this book, which you don't need to read the first 10 chapters in order to read chapter 11. So I thank you for your attention. And if there are any questions, I'd be happy to discuss.
Thank you very much, Gordon, for this beautiful presentation. Is there any question?
Yes.
Please.
Yeah, so I'm of course curious about the theorem in 3 dimensions. So could you give us an idea, how did you prove this?
Yes. So this theorem is part of a long story, actually, which goes back to, well, as far as my involvement is concerned, goes back to about 14 years or so ago, when I started working with David Bridges on the problem of 4-dimensional weakly self-avoiding walk. So without any self-attraction. So there's no L cubed, and the G is positive. So
And
it's-
you're in 4 dimensions, so
And we're
the
in
upper critical dimension.
That's right. And we were interested in computing log corrections.
Right.
And so we used the isomorphism theorem in order to write it as a supersymmetric phi to the 4th model, phi to the 4th and psi to the 4th. And we realized actually more generally that you could work with the n component phi to the 4th model, and that the supersymmetric version corresponds to the case n equals 0. So it's like if you have two bosons, they count for +2 components, and 2 fermions count for -2 components, and the whole thing ends up behaving as if it was a 0 component model. So it's a rigorous way of implementing, de Gennes' observation from long ago that the self-avoiding walk problem is the 0 component spin and vector model.
Yes.
So we did that here in this theorem. That is, we wrote down, we used the isomorphism theorem to write this in terms of the supersymmetric phi to the 6th model, because the local time gets replaced by phi squared. So you get a phi to the 6th from here and a phi to the 4th from here. And more generally, you can think about the n component bosonic problem, which we did. So that's where this n component phi to the 6th model comes in. And it's possible to analyze these simultaneously as a function of n, where the only difference between the n equals 0 case and the positive n case is the perturbation theory has to be done in a slightly different way. But the rest of the analysis is similar. So we've turned this into a phi to the 6th model, supersymmetric in the case of the random walk model. And then in place of that lemma, we have a finite range decomposition of the inverse Laplacian on a torus. So we add a mass actually. And it's a kind of block spin renormalization that we do. So we integrate out scale by scale, and in order to be at the tricritical point, it's necessary to tune the G parameter and the nu parameter exactly in order for the renormalization group flow to a Gaussian fixed point. So the upper critical dimension here turns out to be 3 because the relevant diagram, instead of being the bubble diagram as it is in 4 dimensions, is the theta diagram, like the setting sum diagram. And that diagram has critical dimension 3. It's log divergent in dimension 3.
Yeah, okay, thank you, beautiful.
So, sorry, Gordon, but related to that, so there is no parameter in front of the phi to the 6th in this.
Okay, so loosely stated, so I'm glad you asked that. Yeah, so for this theorem, there's another parameter in front of this L cubed, which we have to take to be small. So we put it. I didn't include it here because for the mean field model, it's not necessary, and it's just one more parameter that doesn't really play any role in the phase diagram. Whereas in this theorem, it's perturbative in nature, and so there's a small parameter here that we called A, and then this GC and the nu C are chosen in an A dependent way.
So the A is going to be, I don't know, much bigger than G or.
A is very small, and G and nu are proportional to A. They go to 0 like A. Yeah.
And there is a running coupling constant associated to this phi to the 6th. I mean, do you have to study the flow of? Is it a
yeah, that's right. We've studied the flow of A, of G. G and nu are relevant variables, and A is marginal in 3 dimensions.
And so the mean field model you studied, that you presented the result, one should think of that as describing what happens just above this the critical dimension.
Or even, yeah, so that's right. But even in 3 dimensions, the tricritical behavior is mean field. So there's no log corrections to, I mean, we didn't prove this, but I think it would be possible to, I hope that it would be possible to study the divergence of the susceptibility and for the spin model for when n is positive of the specific heat as the tricritical point is approached from the dilute phase. And the exponents are, I think they're 1 for the susceptibility and 1/2 for the specific heat without any log corrections. And those are the mean field exponents. So even in 3 dimensions, I mean, it's a nice model in that sense that the mean field theory actually does describe the tricritical point in 3 dimensions.
Yeah, thanks.
The other parts of the phase diagram are much more difficult. So let me see. You know, these points of the phase diagram would correspond to self-avoiding walk behavior, which is completely out of range in dimensions 2 and 3. We have no idea how to prove anything about that. I mean, for dimension 2, it's very tantalizing that SLE 8/3 seems to describe the, I mean, I'm sure it does describe the 2-dimensional self-avoiding walk, but we don't know how to prove that. And, you know, here understanding the critical behavior here would be like understanding in 3 dimensions, would be like understanding the low temperature phase critical behavior of the Ising model in 3 dimensions. So these parts of the curve are very difficult in 3 dimensions, but this part is accessible, which is a little bit surprising because it looks like it might be the most difficult point, but it's the most accessible one of the phase boundary.
Very nice, thanks. Other questions? Okay, so if not, we can thank Gordon again for this very nice presentation. Thank you very much, Gordon.
Thank you.
Thank you.